Erin. Erin is a recent graduate from the University of Washington Computer Science PhD program. But she's not your average techie. Her grad school research focused on developing computational and machine learning approaches to discover genetic elements in methane-consuming bacteria. She previously worked as a data scientist in biotech, aiming to engineer microbes to produce sustainable materials. We wanted a science talk, and we are going to get a science talk. Erin, come up on stage. And I guess stand over there, because...
Hi, everyone. I'm Erin, and I'd love to share a cool story about microbiology and some of the tiny organisms that can help us with our macro-scale climate challenges. So there are many aspects to climate change, but one I think about a lot is sustainability and how we source the materials to make all the stuff we use in our everyday lives. It turns out a lot of stuff comes from biology. Perhaps obviously the flavorful spices in our foods and fragrances in our candles and perfumes, but let's not forget things like silks in our clothes, medicinal molecules and plants, and fuel, which came from a biological source that lived a very long time ago. Many biological molecules have a nice property that nature has saved the instructions for how to make them in DNA. So each of these organisms has some genetic code that enables it to make a useful molecule that we have discovered and incorporated into the products we use. Metabolic engineering is a growing field that aims to manufacture molecules biologically by copying DNA instructions into microorganisms and engineering them into tiny molecule factories. Humans have been using microbes as molecule factories for millennia, for example, using yeast to help us make great products like beer and wine and bread. But what if we didn't want alcohol? Sorry, no offense to the bar at Olmsted, but what if we could engineer yeast to produce other useful molecules? One of the first success stories in this space was to use yeast to convert sugar into artemisinin, an ingredient in malaria medicine. So this plant, the sweet wormwood, naturally has the DNA instructions to produce the artemisinin molecule, which is not present in yeast. But by copying the DNA instructions from the plant and installing them into the yeast genome, researchers were able to funnel resources away from alcohol and towards artemisinin production in the yeast metabolism, which is more efficient to brew in yeast than farm in a plant. And this metabolic engineering process has been extended to all sorts of materials, from solvents to skin moisturizers, jet fuel to fragrances, silk proteins to bioplastics. Nature's catalog of DNA instructions is quite vast. And so this leaves us with a pretty cool equation. With sugar plus yeast plus science, we can make renewable materials, which is especially exciting when you're replacing materials typically sourced from fossil carbon. However, sugar carbon, though renewable, is still a crop, so it competes for land resources with agriculture and natural ecosystem. But what if I told you there exist other microbes out there that instead of eating sugar, they eat greenhouse gas waste? These organisms that eat carbon dioxide or methane naturally, they exist, but they're a little weird, and we're still trying to puzzle together how their genetics and metabolisms work. As a brief aside, Mary Lidstrom is a professor at UW who studies methane-eating bacteria, some of which she discovered right over in Lake Washington. I spent the last 5 years in her lab trying to computationally decode pieces of methanotroph genetics, because wouldn't it be cool if we could devise the same sort of biological production system, but instead of using a food crop as input, we could use a greenhouse gas waste stream? If so, we'd be wielding this double-sided saber of sustainability. Not only are we producing materials with alternatives to fossil carbon, but the input carbon itself is being diverted out of greenhouse gas waste streams and recycled into materials we can use, both of which can help mitigate climate change. Now, I've got good news and bad news. The good news is that there already exist real companies using the science of metabolic engineering to produce real materials. Several of them are using non-sugar inputs, including methane, carbon dioxide, and even an industrial emission stream like steel mill waste gas. It's super cool. This also includes a couple right here in Seattle. The bad news is that even though the technology exists and it works, the economics can be really tough, especially competing with oil-based. I worked at Amyris for 3 years before coming to UW, and I watched the company transition from being a sustainable biofuel company and gradually rebrand itself as a health and beauty company, because the profit margins on making cosmetics or nutritional molecules are so much higher than fuels and commodity chemicals. But there is hope. Just last year, LanzaTech published in Nature Biotech showing that their bioproduction platform using industrial waste gas was actually net carbon negative. And if climate communities can continue pushing on avenues to make the cost of emitting fossil carbon reflect the actual environmental costs that it carries, it will help sustainability-minded bioproduction companies succeed, many of which are on the cusp of economic feasibility, but not quite to profitability. So with that, I'll wrap up and say that I'm hopeful that microorganisms that can convert greenhouse gases into useful materials could be key allies for us as humans shift towards a more cyclical and sustainable relationship with the resources on our planet. Thanks for listening, and feel free to connect. I'm at Erin H. Wilson.